You know those problems that aren't solved with just a quick look? The ones that need you to really sit down, maybe think it through step by step, that kind of careful process.
Absolutely. It's that system two thinking, as Kahneman called it. Slow, deliberate, needs real focus. And, well, getting AI models to do that reliably, that's a huge challenge.
Exactly. And that's right where we're diving in today. We're looking at this really interesting research paper about how these big models, large reasoning models,
Yeah, things like OpenAI's O1 or DeepSeek R1.
how they actually tackle these complex tasks, the ones needing that slow thinking, and maybe more importantly, how researchers are trying to make them, well, better at it.
Right. We've got this paper, and it really lays out the specific issues these models face when they try to reason deliberately,
Mm.
and then it proposes this new framework, something designed to control their thinking process.
Yeah, and the paper even mentions Kahneman, right? Noting how we humans usually think fast first, then slow down if we get stuck.
We do, typically.
But this research suggests the best way for AIs might be, well, surprisingly different.
So our mission here is to unpack these challenges LRMs have with reasoning, with switching gears, and explore this new framework. AlphaOne, they call it IT1.
Okay.
We'll dig into how it's meant to add control, make things more efficient, all based on what's in the source material.
All right, let's get into it. First, just setting the scene. The paper says these recent LRMs, like the O1 and DeepSeek R1 examples, they are showing some progress with complex System 2 type stuff.
Yes, definitely. It's not just about spitting out facts anymore. They're showing they can do multi-step thinking to find an answer. It's this sort of thinking then answering idea.
Okay, so they generate some internal reasoning first, like a chain of thought.
Kind of, yeah. A sequence of thoughts, and then there's usually a specific marker, like a special token. Think is a common one mentioned.
And that tells it, okay, thinking done, time for the answer.
Precisely. And the paper introduces this interesting concept, reasoning progress. They call it P. Goes from 0 to 1, basically start to finish.
Not just how many words, but how much useful progress.
Exactly. It's about actually getting closer to solving the problem. And a key idea they work with, it's in their figure 1, is that slow thinking has a, let's say, smaller reasoning velocity than fast thinking. It's more step by step.
Got it. So you could generate a lot of text quickly, but not get far. That's fast thinking, low progress. Or be slower, more focused, make real headway. Slow thinking, still maybe low velocity per token, but it's moving you forward.
That's the idea. But here's the snag the paper highlights. These LRMs, yeah, they can do the slow thinking, but they're not great at switching between fast and slow automatically.
Knowing when to switch. That's the tricky part.
That's the core issue. Humans, we tend to go fast by default, right?
Right.
And we hit a wall and we consciously slow down. But these LRMs, the paper says, even the ones trained with reinforcement learning to try and manage this, they often end up overthinking or underthinking.
So they can't quite find that sweet spot, that moment to switch gears like we do.
Yeah, it seems like they lack that robust internal trigger that, okay, this is hard, time to shift down mechanism, and that inconsistency hurts their performance on these tougher problems.
They don't have that reliable internal difficulty meter, maybe.
That's a good way to put it, yeah. Now, people have tried to tackle this before, usually at test time, so you don't have to retrain the whole giant model.
Okay, what are the main approaches they tried?
Broadly, two kinds. One is just scaling the thinking phase budget.
Giving it more time or space, essentially. More tokens to think with before answering.
Exactly, more room to work. The other approach is about modulating the slow thinking scheduling, trying to nudge the model to think slowly at specific points.
Like inserting little pause signals.
Yeah, maybe sparsely adding tokens like wait or something similar into the thinking process.
So either give it a bigger sandbox or try to guide its pace within the sandbox.
Right, but the paper points out a key gap.
Mm-hmm.
These methods often look at one thing or the other, either the budget or the scheduling, but not really both together in a coordinated way.
I see.
For example, they mention a method called ESK1 that adds those wait tokens, but it doesn't really manage the total budget explicitly. Then you have something like chain of draft or COD, which limits the steps to cut the budget, but it doesn't focus much on when to slow down within that budget.
So optimizing one lever, but not the whole
You
system.
got it. And this is where AlphaOne or AlphaOne comes in. This framework is designed to modulate reasoning by considering both things, the total thinking budget and the schedule of slow versus fast thinking. Figure 2 in the paper gives a nice conceptual overview.
Okay, so how does AlphaOne actually do that? What are the moving parts?
It really has two main components. The first revolves around what they term the ALMA moment.
Mm-hmm.
This deals with scaling the thinking budget.
Alpha moment. How does that work? Is often just a parameter?
Yeah, alpha is just a number you set, greater than 1. Alpha aims for a thinking phase length that's at least odd times the average thinking length the model usually takes for similar problems.
Okay, so you measure its typical thinking time first?
Right, you estimate that average. And the AO moment is just the point when the model hits that calculated length, 8 times the average. This gives you a scalable, controllable budget. Figure 5 illustrates this scaling effect.
So AV basically tells the AI, okay, aim for this much thinking time, which is deliberately a bit longer than usual.
Precisely. Then the second part of A1 is all about managing how the thinking happens within that scaled budget, deciding when to push for slow thought and when for fast.
And how does it manage that?
Well, before hitting that I moment, A1 encourages slow thinking.
How? By inserting those weight tokens again.
Yes, things like wait or maybe or alternatively. The paper suggests inserting these strategically, maybe after things like paragraph breaks, in the text. And it does this based on some plan.
A plan, like a fixed rule.
It could be. Or something probabilistic, like they mentioned a Bernoulli process, basically.
Mm-hmm.
At each potential spot, there's a set chance, that it inserts a weight token.
Okay, so before hitting the target length, it peppers the thought process with these slow down nudges based on a probability.
Exactly. But now
Mm-hmm.
comes the really interesting part. The key insight, maybe. The second phase of modulation happens after the item moment.
Okay.
After all that work to make it think slow, AlphaOne then actively encourages fast thinking. It pushes for a quick wrap-up and transition to the answer.
Hold on. After making it think more and slower, the strategy is then to hurry it up. That feels totally backward compared to how I'd tackle a hard problem. I'd slow down more when it gets tough, not speed up after thinking hard.
It is surprising, isn't it? But the paper argues this is vital. They talk about overcoming slow thinking inertia. If you just let the model keep adding weight tokens after the I moment, it might just drift.
Keep thinking slowly without actually concluding.
Potentially, yeah. So to force the switch, AlphaOne actually replaces any weight tokens generated after the I moment with the end of thinking token, the think.
So it actively cuts off the slow thought and says, okay, time to answer and no W.
Effectively, yes. It pushes it into the answering phase much faster once that budget threshold is met.
So the whole AlphaOne strategy is set a generous thinking budget on the learn moment, fill that time with planned slow thinking, but then, crucially, force a fast finish once the time's up. Slow first, then fast.
That's it, exactly.
Yeah.
And this counterintuitive approach is what their experiments seem to bear out. They tested I1 on a bunch of benchmarks, math like AME, AMC, coding, science questions from Olympiads.
Across different model sizes too, right? 1.5B, 7B, 32B.
Yes, across that range. And the results are pretty compelling.
So what's the main takeaway from the test? Did it work?
Well, the first big one is confirming that surprising strategy. For these LRMs, slow thinking first, then fast thinking seems to be the optimal way.
Yeah.
Their experiments consistently show the scheduling worked best. It's a real contrast to our usual human fast then slow approach when we get stuck.
Wow. Okay, so for AI, deliberately slow up front, then accelerate. That's a key finding.
It really is. And another major point is efficiency. Even though it encourages slow thinking initially, AlphaOne manages to be pretty efficient overall.
More efficient? How so?
If you look at their Table 1, for the 1.5 billion parameter model, AlphaOne didn't just improve accuracy, it often did it using fewer total tokens on average compared to the standard vanilla LRM.
Fewer tokens for better results. That sounds very practical.
It's a big deal, yeah. Even compared to COD, which tries hard to cut down tokens, AlphaOne often showed a better trade-off, more accuracy gain for the tokens used.
And what about how often it inserts those weight tokens? Did that frequency matter?
It did, quite a bit. Figure 7 in the paper shows this. They found that adding weight more frequently than some other methods, sometimes more than twice as often, actually gave much better performance.
So more frequent nudges to slow down were helpful.
Up to a point, yes. It suggests a denser, more consistent application of that slow thinking prompt is beneficial within that pre-I moment phase.
Okay, let's look closer at the actual performance numbers in Table 1. How much better did AlphaOne do?
Across the board, math, code, science A1 consistently outperformed the base LRM, the S1 method, on COD. For the 1.5B model, for instance, the average accuracy jump was over 6% compared to the base model.
Wow, 6% is significant.
It is. And it was still substantially better than COD, around plus 3%, average and S1 over plus 4.5% average improvement. These gains were generally seen across the larger models, too.
And you mentioned they tested different ways to schedule the slow thinking, the annealing strategies.
Right, figures 4 and 8 show that. They tried things like a constant probability, increasing the probability linearly to simulate fast to slow,
Yeah.
and then a couple of annealing methods, basically slow to fast.
And the slow to fast ones worked best.
Yes, particularly the linear anneal strategy, which aligns with an A1's core idea. It consistently did better than trying to mimic the human fast to slow approach. This really reinforces that central hypothesis about the optimal AI strategy here.
What about that efficiency metric they used, REP?
Yeah, REP, reasoning efficiency performance. Higher is better. It measures how much accuracy you gain relative to the cost, which they measure in thinking tokens.
So it's bang for your buck, basically.
Pretty much. Figures 6 and 9 show I1 generally achieving higher REP, especially on tougher benchmarks like Olympia Bench and Minerva Math for the 1.5B model. It means I1 is getting those accuracy gains more efficiently than the other methods.
It really sounds like all the pieces of I1 matter. What about that last part, forcing the fast thinking after the I moment? Did they test leaving that out?
They did. That's the ablation study in Table 2. They took out just that step, the one where white gets replaced by think after the IRA moment. Performance dropped quite significantly.
Okay, so that really is critical.
Absolutely. It shows you can't just give it more budget and tell it to think slow. You need that mechanism to push it towards finishing, to overcome that potential inertia. The whole sequence budget, slow start, forced fast finish,
Yeah.
that's what makes it work.
It's the complete package. Not just slow thinking, but managed thinking.
Exactly. They also noted, maybe less surprisingly, that the specific token used matters. Weight worked best for them empirically, probably because of how the underlying models were trained. That's in Table 4.
And they included examples, right, showing how it helps.
Yeah, the qualitative examples are neat. They show scenarios where the baseline model might go off track, but inserting weight at a key junction seems to steer it towards a more logical, successful path.
Okay, so AlphaOne looks really promising. But what are the catches, the limitations they mentioned?
Well, a few things. First, it's currently quite tailored to these O1-style models that use specific tokens like weight and the think signal.
So it might need tweaking for different model architectures.
Exactly. If future models have different internal reasoning structures or signals, AlphaOne would need adapting. Second, setting that I moment relies on estimating the average thinking length for a given task.
Which means you need some test examples beforehand.
Right. They did it by sampling a few test questions. It's a small setup step, but it's not zero. If you had absolutely no prior examples, picking a good I might be guesswork.
Makes sense. And what about future work? Where could this research go next?
They suggest a few interesting paths. One is looking into more dynamic or even learned scheduling for those weight tokens instead of just a fixed probability.
So the AI could learn the best times to slow down.
Potentially.
Mhm.
Another direction is making the whole technique less dependent on specific tokens like weight, making it more model agnostic. And the big one is extending this idea to multimodal reasoning.
Problems involving images or diagrams, not just text.
Exactly. Where the model has to reason across different types of information at once. That's a major frontier.
Definitely. Real-world problems are rarely just text.
For sure.
Well, this has been fascinating. This look at AlphaOne really highlights the subtle challenges in getting these advanced AI models to truly reason effectively. It's not just about raw power.
No, it's about managing the process. They struggle with knowing when to think fast and when to slow down. And AlphaOne offers this really clever, though maybe counterintuitive way to manage that.
Controlling both the budget, how long they think, and the schedule, how they think within that time.
Right. And that key finding that for AI, maybe slow first, then fast finish, is the winning strategy. That's a huge takeaway. It helps them get more accurate, often more efficiently, too.
Absolutely. And for you listening, this gives a really neat look under the hood, doesn't it? It shows the kind of smart engineering needed to make these powerful tools work reliably on hard problems. It's not just about making models bigger. Optimizing how they think is crucial.
Which does leave you with a pretty interesting thought to chew on. As we figure out how to optimize AI thinking, especially when the best strategies for them seem different from ours,
Yeah.
how might that knowledge eventually feed back? Could it change how we think about tackling complex problems ourselves?
Something to definitely ponder.